Hi everybody, Dr. Jensen for CCJ 3701 Research Methods in Criminology. I'm going to try to talk a little bit quicker because you can read faster than I can talk, but we are going to do some practice in this lecture so you get a chance to see how things work. I know it's been a rough ride for some people trying to get software, trying to get caught up, getting into their first lab, trying to open the data file, trying to find the data file. It's a little rough, but again, welcome to the world of data analysis. This stuff is actually very typical, and it's a little uncomfortable for a while, but you get better at it the more you do it. And sometimes I call it jumping into the deep end of the pool and learning how to swim. I try to teach you how to float and survive, because sometimes you're in a less than ideal situation, especially if you work in government, military, nonprofit. You'll get all kinds of stuff that you just have to figure out with little time and no money. So anyway, I've worked in government and nonprofit myself, and I know how that goes. So anyway, we're going to do data management and cleaning, and I will tell you this is a really important lecture because it's going to save you time on your labs. It'll teach you some good habits and practices to do whenever you get data so that you're familiar with what you're analyzing and you know what's in there. The more time you spend on something you don't know, the more time you waste. So this is just a series of good habits that will prevent some headaches in the future. So let's jump in. Okay, effective data management and cleaning involve procedures and processes, a state of mind and a way of thinking, never trusting your data, especially if you did not collect it yourself, attention to detail, routines, and systematic checks and rechecks. So you just have to kind of look at it with caution. So you may be given data from an employer, from your boss, from court, from the UCR, a zip code of crime rates, and someone says, I need an answer on this by Friday. Here you go. Here's some data. Figure it out. If you didn't get the data yourself, realize there might be some things in there you're unfamiliar with, you don't know, there might be errors, and you wouldn't want to waste time on data that's bad. So an expression you'll hear in class is garbage in, garbage out. If you have garbage data or data with errors, analyzing it's not going to do you any good because it's going to be a bad result that's inaccurate. So we're going to teach you how to find this stuff out about your data, and you can kind of practice this in Ad Health if you want to. So, 2 facts in the world of quantitative research or working with data. Every data set contains some errors. Every data analyst wastes time drawing the wrong conclusions because of errors they did not find or they disregarded. So we're here to help prevent that so you don't waste time on labs that are painful, right? Data management and cleaning are essential. Anybody can do statistical analyses. Once you learn the concepts and the principles and you get some good practice, anyone can do them. Results are totally meaningless without a clean data set. So you always approach your data for the first time in the same way. So it's a 2-step process. First, you detect the errors. Maybe you're assigned a variable or you find a variable you want to use. You got to go look it over, get to know it, see if there are any errors. It may be just fine. If you do find errors, you got to know how to fix them. And there are certain things we do to do that, which you will learn here. So first, common source of error. Missing data is most often coded using 9s, negatives, 8s, and sometimes 7s. So it doesn't matter what field you're in, whether you're doing government, military, you're in biology or sociology, doesn't matter. Data management is very universal. So anytime you have on bullet 2, not applicable, blank, non-response, missing, so someone doesn't want to answer a question, they said, I don't know, but they gave you some kind of miscellaneous answer that doesn't fit in a valid response. We're going to code those with 9s, 8s, 7s, and negative numbers to kind of help the data analyst know, set this aside, because you can't analyze a not applicable. You can't analyze an I don't know or a skip the question. It doesn't tell you anything. It just tells you they didn't provide a response. Sometimes those are coded as 0 inside the list of values that provides the response. I don't like that because we use zeros for certain kinds of recoding things I'm going to teach you, and so it actually creates an extra step. So a good data analyst knows don't use zeros for that purpose to represent missing data, but I think some people use a 0 because they think 0 is the absence of value. I'm going to use it as missing. I understand why they'd be tempted to do that, but we use 0 for other purposes when we do statistics. So just keep in mind you may find a 0 that's representing a category of information inside a survey question or a response. Data entry errors by staff inputting observations and responses. So these are typing it in wrong, maybe a column shift, data's in the wrong column, they tabbed over and they didn't realize it, or fabricated data. Maybe they made it up and it's fake. Who knows? That stuff happens, I assure you. So let's look at an example. This is missing data coded as 9s, 8s, and 7s. So you're going to see something like this. So question 31. Satisfaction variable. How would you rate your representative's knowledge of the product? Circle 1. So this would be off a survey from maybe an experience at a store or something like that. So you can see they have 1, 2, 3, 4, 5, excellent, very good, good, fair, poor. And then they use -9, -8, -7 for refused, I don't know, not applicable. Again, that's what you should be looking for in the coding. So that's perfectly fine to have it set up like that. So if you ran descriptive statistics for this variable, you wanted to see what the average satisfaction level was for their sale or some other information about it, and you got this result, this would be bad. So take a look at this. The mean is 0.461, the median is 4, the mode is 4, the standard deviation is 6, the variance is 36. Doesn't mean a whole lot to you right now, but let me give you a shortcut. If this is an evenly distributed variable, the mean, median, and mode should be the same or about the same. Look at how far off that mean is from the median and mode. 0.461 instead of a 4. That's a red flag. So that tells you something is tugging on that mean and making it less than what it is. So this is how you would detect an error. So the first thing you do, anytime you go start working with a new variable you've never worked with before, run descriptive statistics on it. Go look at the mean, median, mode. If it's an interval variable, it has numbers inside it that you can quantify. If it's not, if it's more of like a category variable, yes, no, race, gender, or it's a ordinal one that kind of has degrees of something happening or more or less, you can run frequencies on those and look over the data and see if there's any weirdness like this going on in there. This is the kind of stuff you look for. So if we did that, this is what we might see. So there's that mean, median, mode, standard deviation, variance again. If you look at a frequency, which is the next part, observation 1, 2, 3, 4, 5, 6, 7, satisfaction. So the satisfaction column would be the actual response. They gave a 4, they gave a 5, or whatnot. So if we go down that list, you actually see -8, -9 inside the list. Here's the problem. They use -8s and 9s properly to represent an I don't know response, a not available, or refused, but they didn't tell SPSS to treat that as a missing piece of data and not include that in the calculation of the mean. So basically, when SPSS is calculating the mean, it's including those negative numbers in there. So it's adding the 4s, the 5s, the -8s, and -9s, and then creating a mean off of that. That's why that mean is so tiny. It's got negative numbers in there. So you have to tell SPSS, treat those negative numbers as missing data and exclude them from the analysis. They're not an actual number. They're just kind of a placeholder to say this is an I don't know response and we're not going to analyze it. So that's the kind of stuff we're talking about. This is a very easy error that I see all the time where somebody didn't identify the missing data properly and suddenly you're calculating this really wonky mean because it's treating the number as the actual number rather than a category for something that was an I don't know response or missing data. Okay? So that's one way to detect the error. Here's another example. What is your current age in years? Okay, so we go, okay, I want to work on a variable called age, and let's run some descriptive statistics on it. So we get something that looks like this. The mean is 38.15, the median is 19, the mode is 1. That's really weird. Again, you'd have to know the source of your data. Do I have 1-year-olds in here? Is that normal? Are these people supposed to be over the age of 18, just adults? So you'd have to go look at the methodology, the summary. Who was included in the study? Was it adults and children? And is that even right? But look over at the observation and the age column, okay? Do you see any problems in there? Yes, right here on row number 4, 225. Someone put 225 years old. Okay, unless they're supernatural, that's not possible. So clearly somebody typed it in wrong. And obviously a large number like that is going to tug at that mean and make it inaccurate. Okay, so we don't know if it was really supposed to be age 22, if it was supposed to be age 25. We're not really sure. Okay, doesn't really matter what it's supposed to be. All we know is we can't analyze it this way because it's going to be wrong. Okay? So this is the kind of stuff I'm telling you about. You don't have to look at every observation. The mean would tell us when it's off from the median and mode that something's going on that's a little weird. And that's when we would go in the frequency, start poking around a little bit. So here's what it would look like if we graphed it. Okay? So we call this measurement error. Random error or systematic error is normal. Okay? So even if we're a little bit off from what we hoped we'd find, maybe we were surveying a population of people and the true average age of that population was 47 and the group that we got was actually 38, that's okay because it's still, it lets it have the similar kind of shape it should have, so it's still accurate. And we call that random error. The distribution of X with random error, it doesn't make things too crazy. It's actually all right. But if we get something totally different, then we've actually shifted that average. Okay, we call that bias or systematic error. That's just due to some bad value in there that's making it wrong. So we're here to teach you how to detect from just random error, which is normal, which we test for in statistics, versus systematic error, meaning there's a problem in the data that's going to make it inaccurate. Again, doesn't really matter the nature of the error. You need to find it and fix it. That's how you need to focus. So once data are collected, ready for analysis, you need to be able to find these and then fix them. Okay, so most errors can be detected using 3 different ways, and these are the good habits you need to use whenever you are looking at new data or a new variable, which you're going to encounter in your research project and the labs we do. So it might be good to pause and write these down and kind of put this in your notebook. Number 1, descriptive statistics, which I just showed you. Run frequencies on these variables, see what's in there, get to know it. Number 2, a logic check. Is it making sense what you're seeing based on what the variable is supposed to represent and the answers that are contained in there? And then number 3, an expected association or relationship. Okay, it should be occurring this way because these 2 things tend to relate to each other. Okay. If you wanted to add a number 4, you could read the code book, okay? Go read about the study, read about the variable, and see if you can get the actual question wording from the survey so you know exactly what was asked and exactly how people answered. Now, in the world of government and military, you may or may not have a survey. You may just be given a set of data that came from some kind of database, right? So there is no code book. You still need to be able to understand how the data came in so you know what's represented in there. All right, so descriptive statistics, what do we mean by that? Those are things like frequencies, the minimum and maximum, the range, the mean, median, and mode, things like scatter plots and histograms like you see in these 2 graphs. So you can graph out stuff and see if there's a normal curve shape to it like you see here. You can check that mean, median, and mode. You can check the frequency to see if there's any unusual values. So again, this is just you getting to know the variable, okay? So again, look for those zeros, the 999s, the negatives that are mistaken as a response rather than to represent missing data that should be excluded. Another key is to look for a standard deviation that's higher than the mean value. That is actually mathematically impossible. So if you see a result that looks like this, the standard deviation is 59 and the mean is 38, that's a red flag, okay? It should always be smaller. Always, always, always be smaller, okay? Here's another one. Here's a histogram. So this is if we kind of plotted out everybody's responses. Again, you have to get to know the data you're studying. So here we go, children's age reported by the caregiver. Okay, so we have at the bottom the age of children 0 to 54, where we go, well, that doesn't make any sense. I don't know any 54-year-old children. Here's the thing. You got to get to know your data. So you might say, okay, Jensen, red flag, this data can't be real. There's all kinds of funny little bars that are really, really high and some that are really low. This doesn't look normal. Here's the thing. This is age in months. If you've ever worked with children, you've learned that we record their age in months. So 6 months, 12 months, 18 months, 48 months, that's a 4-year-old. Okay, so that's also why you see some little peaks, because people tend to remember their children's age 18 months, 24 months, 36 months. And that's why you see more people in that response, because that's a little more familiar to them. They might not remember their kid is 47 and a half months. They may just say they're 48. Okay, so we'll continue on in the next lecture. Thanks.